Welcome to this explainer. You know, for decades, the tech industry has been building data centers to essentially act as giant, highly efficient digital filing cabinets. Their main job was to store, retrieve, and route data. But honestly, that era is effectively over. Today, we're no longer just building data centers to store data. We are building massive, vertically integrated factories to manufacture intelligence. Okay, let's dive into this. Today, we're looking at 5 key areas: the evolution of compute inside the AI factory, the power and cooling crunch, the next 5 years, and finally, the new IT playbook. Section 1, Evolution of Compute, a brief history. Think about it. Every era of computing basically solves a specific resource problem left behind by the last. If we track the last 60 years of history, you'll see the 1960s were all about mainframes. Compute was purpose-built and totally siloed. One application, one physical machine, which naturally meant massive underutilization. By the 2000s, virtualization solved that. We decoupled the operating system from the physical box, giving us elastic virtual machine hours. Then the 2010s hit, and hyperscale clouds solved the problem of global scale and reliability. But then, in 2023, the rise of large language models completely broke the mold. The AI factory was born out of absolute necessity, and it's a structurally different environment from literally everything that came before it. Section 2, Inside the AI factory. Let's move to how it works today. Training these massive models exposed a really fundamental mismatch. Traditional cloud facilities were built to run millions of lightweight, diverse virtual machines on standard CPU cores. But AI workloads? They are dense, incredibly power-hungry parallel matrix multiplications running at massive scale. It's essentially doing millions of complex math problems all at the exact same time. To pull that off, thousands of chips, like NVIDIA's Blackwell or AMD's MI300, they can't act as independent servers anymore. They have to act as one single coherent machine, tightly coupled together via high-bandwidth interconnects like NVLink. A facility built for lightweight VMs just absolutely cannot handle that kind of synchronized computational density. So the crucial point here is that we have to completely reframe how we view these facilities. The AI factory is a full-stack production system that manufactures intelligence at scale, transforming raw data into real-time insights. It's a revenue-generating engine now. And because of this economic reframe, the old metrics of success are out the window. Today, token throughput, cost per token, and most importantly, tokens per watt, well, those are your new fundamental units of account. And that brings us to the stark physical reality of all this new compute density: 140 kilowatts. A single rack running these tightly coupled GPUs now needs to dissipate around 140 kilowatts of heat. That is an enormous amount of thermal energy. To put that into perspective, it's like turning on 70 household ovens on broil and stuffing them all into a single server closet. It's an incredible physical burden that traditional air cooling systems, the giant fans blowing cold air through raised floors that we're so used to, they simply can't handle it anymore. And this brilliantly illustrates the direct consequence of that heat burden. Just look at the incredibly steep adoption curve for liquid cooling. Liquid-cooled AI servers jumped from being about 15% of deployments in 2024, scaling to 54% in 2025, and they're projected to hit roughly 76% in 2026. Because AI factories unify energy, chips, and infrastructure into one single system, the physical building itself actually has to be co-designed with the silicon. You can't just wheel a server into a room anymore. The plumbing literally has to be built right into the architecture. Section 3, the power and cooling crunch. The physical limits. The scale of investment happening right now is, well, it's almost difficult to comprehend. Hyperscalers, we're talking companies like Amazon, Alphabet, Meta, Microsoft, and Oracle, they're projected to spend an astonishing $660 to $690 billion on AI data center expansion in 2026 alone. They are racing to deploy AI capacity that they can sell almost like a public utility, offering GPU hours and token throughput service-level agreements. But you can't spend that kind of capital without eventually hitting some very real-world walls. If we zoom out to the macro level for a second, the true bottleneck becomes incredibly visible. Gartner estimates that global data center electricity demand will actually exceed 1,000 terawatt hours in 2026. This is a staggering amount of electrical draw, and it's fundamentally straining power grids all across the globe. To give you an idea of that scale, 1,000 terawatt hours is roughly equivalent to the annual energy consumption of the entire country of Japan. It's wild. Back in 2024, the major bottleneck was just getting your hands on the chips. But by 2026, the GPUs are finally available, but the electricity to run them is not.
power becomes the primary constraint, not chips. Gartner projects that by 2027, 40% of AI data centers will be physically power constrained. The grids simply cannot supply the electrons fast enough to match the silicon we're producing.
Section 4. The next 5 years. The geographic shifts. Because power is the absolute bottleneck right now, the entire playbook for where to build infrastructure has completely flipped. The old site selection strategy prioritized building near users, relying purely on local grid interconnects. But the new site selection strategy, it prioritizes building near power, period. Winning strategies right now are focusing on direct investment in power generation. Think nuclear plants, next-generation small modular reactors, and on-site gas peaker plants that can just generate power on demand. Being close to the energy source matters way more than being close to the end user for these massive training clusters. But what happens after a model is actually trained? That's changing too. NVIDIA has basically come out and declared that the training era is over, and the inference era has begun. What this means in practice is that while massive, centralized campuses will still handle the initial training of these models, the day-to-day use of the AI, the inference, answering user queries, that's going to decentralize. We're going to see rapid growth in smaller, regional edge facilities that are optimized specifically for low-latency AI queries, sitting much closer to the actual users. As these facilities spread out, the building standards are rapidly evolving alongside them. Closed-loop, non-evaporative liquid cooling is basically becoming the default at scale. For example, Oracle's 2026 AI campuses are deploying closed-loop systems specifically to prevent straining local groundwater resources. Furthermore, because these facilities are just so incredibly complex and unforgiving, pre-deployment digital twin simulation is becoming mandatory before a single brick is even laid. And impartially speaking, as energy demands absolutely soar, we're seeing heightened state and federal regulatory scrutiny over data center energy use and its overall impact on local ratepayers. Section 5. The new IT playbook. Actionable advice. Now, what's really interesting about this transition is that the traditional IT focus on purely software skills is just no longer enough. You absolutely must build power and cooling literacy. Understanding rack-level density and liquid cooling, those are now core IT competencies. You also need to learn GPU-aware orchestration, things like multi-instance GPU partitioning, which lets you slice up a single chip for multiple users, and really master the inference stack to control your costs. Finally, this space moves incredibly fast. Specific chips and cooling standards will easily change in 12 months, so you have to treat vendor documentation as living references, not just a one-time learning exercise. So for immediate action, you're going to want to follow these 3 steps. First, reassess your providers not just on compute contracts, but on actual power availability and interconnection timelines. Power is now a massive procurement risk. Second, overhaul your FinOps. Your financial operations and cloud cost governance need a serious update. Your old cloud dashboards built around VM hours are simply not going to map cleanly to GPU seconds and cost per token metrics. And third, simulate your infrastructure digitally before committing massive capital, because retrofitting a facility for AI density after the fact is just incredibly costly. We've moved from the mainframe to the elastic cloud and now right into the highly dense, physically constrained era of the AI factory. The metric of success is no longer just uptime, it's tokens per watt. So I'll leave you with this one vital question to consider as you evaluate your own organization's readiness. Is your infrastructure truly ready to manufacture intelligence? Thank you so much for joining me for this explainer, and I will see you next time.